All right, so we were looking at polynomial stuff, right? Did I show you guys did we look at the polynomial graph yesterday where we looked at like we zoomed way out? We did do that, okay, good. Okay, so next issue is turning points. When we talk about the graph of a function, the turning points are the places where it turns from increasing to decreasing or decreasing to increasing, right? So here's an example of a turning point. If a couple ways you can think about this. If we know what an increasing function is, right? An increasing function is one where if you're moving in the positive x direction, you're moving uphill along the graph. So imagine an ant walking on this function. Where it's increasing, he's walking in the positive x direction from left to right, uphill. Here, so it's increasing during this interval, it's decreasing during this following interval right here, where he's walking downhill. In between those two places, he's got a transition from increasing to decreasing. That's called a turning point. In calculus, we talk about that. Instead of calling it a turning point, we call it, and we will in here too, we call it an extremum. It's a maximum. Right? It's a place where we have an extreme value of the function. It's a mountaintop or a peak, in other words. The ant can stand on that point and look around and be at the highest point. Maybe in the distance there's some higher points, but at least locally speaking, right around him, it's the highest point. So we call that, it's a turning point, or we call it a relative maximum. Relative meaning relative to the x values around the ant, it's the highest place. Sometimes we call, instead of a relative, we call it a local maximum, because locally speaking, it's the highest point. If he continues along this function, he's going to decrease for a while, and then he passes through another transition down here back to increasing. So there's another turning point. This one's called a relative minimum. And again, we can also call that a local minimum. Same thing, okay? So what do we have here then? The points at which a polynomial function switches direction are the turning points on the function. If the turning point is higher than any nearby point, it's called as we said, it's called a relative maximum, relative or local. If the turning point is lower than any nearby points, it's called a relative minimum or a local minimum. Maximum and minimum values are called extrema. And that's just plural for extremum. Plural for extremum is extrema. In other words, extreme values. Okay, turning points define where the function is increasing or decreasing because they're the boundaries. We would say that on this function increases to the left of the relative maximum and to the right of the relative minimum, right? Those are the places where the ant is walking uphill. The function is decreasing to the left of the maximum and, sorry, I said that backwards, to the right of the maximum and left of the minimum. So between the two would be the interval where it's decreasing. Okay, give me 1 to 5. How are we doing? Is that all making sense? Okay, just some kind of vocabulary. Okay, so now a polynomial of degree n can have at most how many turning points do you think? Let's just explore this a little bit. Let's look at a couple examples in Desmos. Let's take some examples of, how about quadratic functions? It's a pretty small sample, but what do you think? Quadratic functions seem to have how many turning points? One, right? They seem to have one turning point. Okay, let's try this with cubic functions and see what happens. There's one. Okay, there's a cubic function. Okay, there's another one. There's another one. And here's one more. So if I look at these, let's just look at these one at a time. So there's a cubic, right? How many turning points? Two. There's a cubic. How many turning points? Okay. There's a cubic. How many turning points? Are there? Does that one ever, it looks like it's decreasing the whole time, doesn't it? It never turns around and increases. Okay. And there's another one. That one looks like it's always increasing. Okay, so then let's see if you can make a guess here. A polynomial of degree n can have at most how many turning points, do you suppose? So our cubic, that's a third degree, right? What's the biggest number of turning points we had for our cubic function? 2, okay. Let's try one more example. What if we try a quartic? Let's try a fourth degree polynomial. Okay, how many turning points does that have? 3. Now I can make one that doesn't have 3. There's one that the green one only, whoops, the green one only has 1, right? But what do you think? What do you think the maximum number of turning points a quartic can have is? Okay, so what's the relationship then? Yeah, n minus 1. Does that make sense? So if it's an nth degree polynomial, the biggest power of x is n, then the very largest number of turning points that it can have is n minus 1. Okay, it doesn't have to have that, but it could. Okay, so what about real zeros? So real zeros are the points at which the function intersects the what? You fill in the blank for me. Yeah, the x-axis. The real zeros are the points at which the function intersects the x-axis. Then that makes the real zeros, and we've mentioned this before. What's that mean another name for real zeros would always be? If the real zeros are they're the places where the function is guaranteed to intersect the x-axis, what's another name for real zeros? X-intercepts, right? Okay, so that's always going to be true. Are all of the zeros of a function guaranteed to be x-intercepts? No, not necessarily, because we know that we can have complex zeros, complex solutions if we set the function equal to 0, meaning complex zeros, that have imaginary parts. And those, remember, do not correspond to real zeros. And we looked at an example of that, and we've gone back to this several times, I believe. But if I graph a parabola like this that has no x-intercepts, then that means how many real zeros does that quadratic function have? 0. Yeah, it never has an x-intercept. So both of the zeros of this function have imaginary parts, right? They're complex with imaginary parts. Okay, so a polynomial function of degree n can have at most how many real zeros do you suppose? We can go back to our example here, our Desmos examples, and I can tweak these a little bit. Let's look at, let's look at the blue one, and I'm going to do something. I'm going to do this. I'm going to subtract I'm going to add 0.5. How many x-intercepts does that have? Looks like there's, what, 4 of them? Okay. Oh, you guys can't see that. Whoops. Yeah, okay. Okay, everybody agree? There's a quartic function. It looks like it's got 4 x-intercepts, right? Now I can tweak that a little bit. What if I do something different, like I do like that? Now how many does it have? 2. Okay. Right there and right there. And I could even go, what if I go, I think if I just do that, now how many does it have? 3. But what do you think the most is it could have then? Yeah, 4 seems to be the most, right? If it's going to have 3 turning points, the most it could ever have is 4. It could have less than that. And if I look at a cubic function, I'll see the same kind of thing. Okay, I could create, right now this one appears to have 2, right? If I were to just shift this down just a little bit, I could create a cubic function with 3, but that's the most I could get, isn't it, with 2 turning points? Okay, so then what's our pattern? A polynomial function of degree n can have at most how many real zeros? N, yeah. Okay, so now let's just practice with this a little bit. We've just got some new relationships here about graphs of polynomials. Use the graph of the polynomial function shown to complete these questions. Let a be the leading coefficient of the polynomial. So determine the number of turning points and estimate any x-intercepts. How many turning points do you see? 2. Okay. So the number of turning points is 2, and estimate any x-intercepts. Well, what do you think? What's the x-intercept? -2, sure, right there. Okay, so it looks like right there we get 1 x-intercept. Is the leading coefficient positive or negative on this one? Positive. How do you know? It matches the behavior, doesn't it? It matches the behavior for an odd degree polynomial. It should be up to the right and down to the left, which this one is, if the leading coefficient's positive. So in this case, a is definitely positive, greater than 0. Okay, what's the minimum degree of that polynomial? Could be bigger, but it has to be at least what degree polynomial? It's got to be at least 3, doesn't it? Based on the number of turning points. Even though it's only got 1 x-intercept, that would mean it has to be at least linear. Obviously, that's not linear. But the fact that it has 2 turning points means it has to be at least 3rd degree, right? Give me 1 to 5 on that. Does that make sense? Okay, let's try a couple more of those. So the turning points are telling us n has to be greater than or equal to 3. It's at least 3. Okay, let's try, how about that one? Try that one on your own. Answer all parts of that. What do you think? What about the last part? What do you think? What's the minimum degree on this one? 2? Anyone got a different answer? Two based on which number? On the number of x-intercepts or turning points? How many turning points are there? Okay, so we get 3 turning points right there, there, and there, right? How many x-intercepts? Well, I guess that's still part of A. How many x-intercepts do we get? 3. There, there, and there. Okay, is A positive or negative on this one? Negative, yeah. It's negative because end behavior is down on both sides. That would be a negative even, right? So we know it's an even polynomial, it's even degree polynomial, but what's the minimum degree have to be? Based on the number of x-intercepts, we'd say 3, right? But obviously this is an even degree polynomial. It can't be a degree 3 polynomial. It's got to be bigger than 3. So 4, right? Based on the number, even the number of x-intercepts tells us that. What about the number of turning points? There's 3 turning points, so what's that tell you about the minimum degree? It's got to be 4, right? Because remember, the maximum number of turning points is always 1 less than the degree. So if I'm getting 3 turning points, that means the degree has to be at least 1 more than that. So for part C, n has to be greater than or equal to 4. Okay, give me thumbs. Is that making sense? Okay, it's kind of like we're doing a puzzle here. Okay, how about this one? For this function, what's the maximum number of real zeros that function could have? Could have 8, couldn't it? Because the degree is 8, right? So I could have up to 8 real zeros. What's the maximum number of x-intercepts that it could have? Well, 8. They mean the same thing, don't they? Those go together. What's the maximum number of turning points that it could possibly have? 7. Okay, so then moving on, just extending this just a little bit more. So the multiplicity of a 0, should I make that a little bigger? Is that hard to see in the back? I think I can make that a little tiny bigger. Oops. Okay, so the multiplicity of a 0 is equal to the number of times that its corresponding factor occurs. So what does that mean? So like if we were to take this polynomial up here, now this is a cubic polynomial, but we could factor this. This is one, we're going to get into some polynomials really soon that we don't yet know how to factor. We're going to have to learn a couple new, I mean, they're not really very new, but we got a couple new techniques for factoring polynomials that we haven't learned. This one we can do though. F of x equals x cubed minus 6x squared plus 9x. How would we factor that? We haven't factored stuff in a little while, but it hasn't been that long. What am I going to do? What do I always try to do first when I'm factoring? What do I always try to do first when I factor? Yeah, I want to undistribute a GCF, right? So is there anything I could undistribute there? I could undistribute an x, okay? So if I take an x out of that, what's left behind? X squared minus 6x plus 9, okay. Good. So the x is done, that's linear. Can I go any further with this? Are there magic numbers that multiply to 9 and add to negative 6? Negative 3 and negative 3, right? So I could rewrite this then as x times, oh man, I keep getting my colors wrong here. X times x minus 3 times x minus 3, which is the same thing as x minus 3 squared. Aha. Okay. So now what are the zeros of this function? If I set this polynomial equal to 0, what are the zeros? Think what the zeros are, right? The zeros are the values of x that are going to make the function equal to 0. What would they be? Three is one of them. Yeah. How come? Well, because I'm just going to apply the zero product property, aren't I? I know that the product of factors can only equal 0 when I'm multiplying by 0, right? So I know that I'm going to get 1 0 from that factor, which is x equals 3, right? Okay, what's the 0 of the blue factor? What value of x makes that blue factor equal to 0? 0, right? Okay, so we also get the factor x equals 0. Okay, those are my two zeros. X equals 0 and x equals 3. Okay, what are the multiplicities of those? What's the multiplicity of x equals 0? How many times does that factor occur? 1. What's the multiplicity of x minus 3? How many times did we get the factor x minus 3? We got it 2, didn't we? Right? How do we get that? Well, it's the exponent, right? The exponent of the factor tells us how many times that factor occurred when we factored. If I wrote this thing out without squaring it, wouldn't I just have gotten f of x equals x times x minus 3 times x minus 3? Because Trey told us the magic numbers were negative 3 and negative 3, right? So I get a factor for each of those magic numbers, but we choose to write that as x minus 3 squared. So the multiplicity of 2 is better seen just in the exponent, right? Everybody get that? You get the idea of what multiplicity means then? Multiplicity is just telling us what's the power of each linear factor. The number of times it's occurring means what is its power when I write it in a simplified form, okay? So how does this affect a graph? Okay, let's see, let's graph this function and see if we can determine if the multiplicity has any impact on what the x-intercepts look like. Does anybody want to make a prediction? We know we're going to have x-intercepts where on this function? On f of x. 0 and 3, right? We said real zeros always correspond to x-intercepts. So we're guaranteed to get x-intercepts at x equals 0 and x equals 3. My question to you, and what we're going to answer for ourselves here in a second, is what's the nature of those x-intercepts? Does the multiplicity, because this is a multiplicity of 1, let's write that down. And this is a multiplicity of 2. Does a multiplicity of 1 look different than a multiplicity of 2 when we actually look at the x-intercepts they produce? Anybody want to speculate what the difference is? You can be wrong. Does your intuition tell you anything here? Okay, let's see. So there's our function. I'm going to delete all this stuff. Okay, there's our two x-intercepts at 0 and 3. Okay, 0 was, whoops, our blue one, right? And 3 was our green one. So what do you think? What's the difference? What is the multiplicity of 1, the blue x-intercept? How does that differ from the x-intercept where the multiplicity corresponding to a multiplicity of 2, the green one? What do you notice? It's a turning point. Yeah. Yeah, if the multiplicity was 2, we got a turning point. Okay? Let's experiment a little bit more with this. Okay, what if we build a new graph here? I'm going to write a polynomial in factored form this time. Like we could have written this last one. If we wrote it in factored form, it would have looked the same. It just would have been x times x minus 3 squared, right? Same function we had before, okay? Okay, Grace, pick an x-intercept. Where do you want this thing to cross the x-axis? 4. Okay, so how am I going to create an x-intercept of 4? What does the factor need to look like? Well, it could be x minus 4, right? Or any power of that. Okay, so let's do x minus 4. Oops, that's not 4. X minus 4. And if I square this thing, now if it's linear like that, if I just leave it with a multiplicity of 1, look, it cuts right through the x-axis. If I make it squared, now, what do you know? It does the same thing. It acts as a turning point, doesn't it? Okay, let's create another x-intercept. Where do you want this one to be? What do you think, Tabri? Where do you want your next x-intercept to be? -2. Okay, so what's the factor that's going to give us an x-intercept at -2? X plus 2, right? Because zeros correspond to x-intercepts. In order to get a 0 of -2, I would need a factor of x plus 2. And we'll talk more about that relationship later. Okay, if that's to the first power, it cuts right through. What if I make it to the second power? It's going to be another turning point. Everybody see that? Okay. What if I make it to the third power? What do you think it's going to do? Interesting question. What if it's to the third power? I'm going to stretch this out just a little bit. So there's my function so far. I'm going to tame this a little bit and multiply it by 0.2 so we can see it a little better. Okay. What if I make that cubed instead of squared? What's it going to do to that x-intercept at -2? Anybody have an idea? It's going to look like an odd degree. Let's try it. Let's try it. So if I make that a 3, hey, what do you know? Look at that. Now, what's that? If I kind of focus in on this x-intercept, doesn't that look an awful lot like a cubic function? Just x cubed? Agreed? If I focus in on the other one over here, doesn't that just look like a quadratic? Doesn't that look like x squared? Right? Well, what if I make one, what do you suppose is going to happen here if I make one that, like I'm going to put one at x equals 1. And I'm going to make this to the 4th. What do you think that's going to look like when I show you that graph? It's going to look like a quartic, isn't it? There you go, doesn't it? If I zoom in on these, and again, I'm going to make this a little smaller. Let's make that 0.05, or how about 0.1? Okay. What happened there? So look, there's my, at x equals -2, as we saw, that looks like a cubic polynomial. At x equals 4, it looks like a quadratic polynomial. And at x equals 1, it's more squared off. It looks like a quartic, doesn't it? Okay? So that gives us some really interesting information. That tells us that when we're looking at the multiplicity of a polynomial and we graph it, zeros act like their parent functions, right? If the multiplicity is odd, then the graph, a couple different ways you can say this. What I like to say is it's going to cut the x-axis. It cuts the x-axis at that 0 because all odd polynomial parent graphs cut through the x-axis. If the multiplicity is even, then the graph bounces at that 0. It's going to act like a turning point. Okay, now it could bounce from the top, or if I wanted to, like it can bounce from the bottom, right? If I did something like this, if I change this to a negative, same behavior holds, only now they're just bouncing against the bottom of the x-axis. Doesn't matter, right? Okay, give me 1 to 5. Is that all making sense? Okay. And that gives us a pretty powerful tool for just sketching graphs of polynomials, which is usually all we want to do. So make some predictions here then. We want to, for these few examples, we want to identify what the zeros are going to be, what their multiplicity is, and what the effect is going to be on the graph. Okay, so number 6, give me a0 of the function there. What do you think, Melanie? What's a0 of this function? Give me one of them. 4, okay. What's another 0 of this one? What do you think? Ashley, what's another 0? -7. And should get one more out of that. What do you think? Ashton, what's the other 0? Negative 1/2. Good. If I set that factor equal to 0 and solve, I get the 0, negative 1/2. What's the multiplicity of the 0 at 4? 3. Okay. So what's that mean? What's going to be the effect then? What's that going to look like when we graph that x-intercept? It's going to cut the x-axis, yeah. So it's going to cut. And we could even make a prediction kind of what the basic shape is going to be. What's the basic shape going to be? If it's cubic, isn't it going to look like kind of like that? Now, it could be, we don't know the direction. It might be flipped, but it's going to have that cubic shape to it, right, when it cuts through. Okay, what about the 0 at negative 7? What's going to be the multiplicity of that one? 2, okay. So what's the effect going to be then? It's going to bounce. So we know it's going to do something like that. Now, it might open down, right? Could open down instead of opening up, but we know it's going to bounce. And then the one at negative 1/2, what's its multiplicity? It's 1. Good. So it's going to cut like a line, isn't it? It's going to cut like that. Okay. All right. So now let's go one step further. Let's try to make a sketch of this thing. Okay. What's going to be the overall? I want to know what the leading term of this polynomial is going to be. So in other words, if I wrote this thing out, if I expanded the whole thing out, I want to know what's going to go there. I know that after that, I'm just going to get a bunch of other junk. But the only term we care about when we're looking at the large-scale behavior of this thing, when we're looking at the end behavior, is the leading term. If I expanded this whole thing out, what would I get? I'm going to get, it looks like I'm going to get from this one right here, if I were to take each of these separately, here, let me do this. I need a little more space for this because I really want to make this point. Oops. Okay, so if I were going to take the x minus 4 cubed, and we're going to expand out that whole thing, that's going to be x minus 4 times x minus 4 times x minus 4, right? Would everybody agree when I do that, I'm going to get x cubed plus a bunch of stuff, right? Okay, this green one is just 2x plus 1 to the 1. And what about the orange one over here that we had? If I expand that out, I'm going to get what? X squared plus stuff. So when I multiply this whole thing out, what's going to happen? Well, I have to multiply these in pairs. So when I multiply those two out and I FOIL it out, or I distribute, aren't I just going to get 2x cubed plus junk? Everybody agree? Okay, and when I multiply that by the blue one, which is x cubed plus stuff, now what am I going to get? Yeah, I'm going to get 2x when I make that distribution. My leading term is going to end up being 2x to the 6th plus a bunch of other stuff, right? So then the leading term is 2x to the 6th. We know what the end behavior is going to be, don't we? We know the end behavior if we have a positive leading coefficient and an even degree. It's doing that, isn't it? Okay, we'll pick this up tomorrow and then I'll let you work on this.